Alright, so in our next lesson, we are going to talk about iodoform tests. And we are talking about iodoform tests. It's actually one of the most common tests in our laboratories that we use to identify methyl ketones. So when we say a methyl ketone in the first place, what do we mean by a methyl ketone? For instance, if you are having your carbonyl group, right, one of it must be strictly attached to a CH3 before we can call it a methyl ketone. For the other side, it can be any group. So let me represent it with R. Because of this, I'm having my, let me try and zoom in very well so that you could see what I'm talking about. Because of this, I'm having my methyl ketone. You see there's a methyl group here and a ketone. Now there's a special property about this particular methyl ketones that makes it very accessible to the iodoform test that we are talking about, because iodoform tests are strictly for compounds that have the methyl ketones. Now we can also generate methyl ketones. Then, since we are saying that the methyl ketones are only related to iodoform tests, then someone might ask, we can also have some aldehydes. Here is an exception. It's not an exception per se, but it's one of the special properties of aldehydes, right? Some of the aldehydes are having a methyl ketone, and it's only one of the compound, and that is what I'm referring to as the ethanol. Because ethanol, if I'm to be drawing ethanol, this ethanol is having hydrogen, and this side I'm having my CH3. This is still having a methyl ketone, even though it is an aldehyde functional group, or even though it's having the carbon double bonded to oxygen and bonded to hydrogen. So ethanol is a special case. And also we can have alcohols, right? The reason why we can use alcohols, and the alcohol that we are talking about here is a primary alcohol, and another primary alcohol is only one kind of alcohol that we are talking about, that is ethanol. So let me draw the structure for ethanol. I'm having my CH3 bonded to carbon, OH, and everything here is hydrogen. Because of the conditions and reagent that we use in the iodoform test, even though there is ethanol, it can still give a positive iodoform test, because in iodoform test we require NaOH, a strong base, in the presence of your iodine molecules, or under heat. This is the condition that is required for our iodoform test. Now, this is a strong base. This strong base and iodine, in the presence of the heat, they oxidizes this alcohol to ethanol. So here you see it can oxidize the alcohol straight to ethanol. So your ethanol, because of the condition, will be converted to ethanol. And ethanol, I've already discussed with you here, is having a methyl ketone. For that matter, it is accessible to our iodoform test. So there's one property I just want to show you here. Let me try and write it here. If I'm having my methyl ketone, if this is my carbon, and I'm having my hydrogens, hydrogen 1, hydrogen 2, and a hydrogen 3. Now, all these 3 hydrogens, 1, 2, 3, these 3 hydrogens are very, in fact, they are weakly acidic. They are very, very weak. They are weak because look at what is happening here. Electrons are being pulled off. And where do you think these electrons are going? They are moving to the oxygen direction, because oxygen is having partially negative. Its electronegativity is very high. So it pulls electrons from these hydrogens all the way to the oxygen because of the electronegativity difference. And for that matter, these hydrogens are weakly acidic. So weakly acidic. Then in our condition where our iodoform test, we have a strong base, which is the NaOH, then these weakly acidic hydrogens will be easily deprotonated by this base. So because it is weakly acidic, this OH minus from the NaOH can actually abstract this hydrogen. Abstracting this hydrogen will leave the electrons to this carbon, and now you are going to generate a carbanion here, right? Because the electrons will not move with this hydrogen, they are rather going to fall onto this carbon, making it have a negative charge, and that's what we are referring to as the carbanion. So now let's start with our whole reaction. We are starting with iodoform test. So let me flip it, and now let's start. So with our iodoform test, we are supposed to have a compound that is having your ketone, your methyl ketone, right? So let's say let me choose a compound in mind. I can have CH2 or CH3, CH2, right? CH3, CH2 has been bonded to, my camera is not stable, okay. It has been bonded to a carbon, double bonded to oxygen, and here I'm having my carbon, a hydrogen, a hydrogen, and a hydrogen. You see, I've taken my time to split this because we are coming to do something very serious here. This structure is actually called a propanol, right? Sorry, it's called 2-butanol. So let me write it here. It's not a propanol, 2-butanol. Meaning, in this particular reaction, in the presence of a base, OH minus, that is coming from the NaOH. This is the base that we use, right? It provides OH minus, which is a strong base. Because these hydrogens are weakly acidic, you are going to have this base capable of deprotonating one. So when it abstracts one of the hydrogens from there, what do you think it will happen? Now the electrons will fall back onto this carbon, which is a very interesting idea. Now you are going to have water being formed and our carbanion, which is CH3, CH2, carbon, oxygen, and I'm having my carbon with a negative charge here, and I'm having the two hydrogens. All right, so now see, there can be a stabilization, resonance stabilization, where these electrons can fall onto this, creating a double bond. But the moment there's a double bond, you don't have to leave your reaction like that, or else you are trying to mean that carbon can form 5 bonds, which is not possible. So one of the electrons here is supposed to be broken, fall back onto this oxygen, and now we are going to have our resonance stabilization. So I'm going to draw a hybrid. I'm using this sign because I'm giving a hybrid, which is CH3, CH2. I'm having my carbon, and now here O minus. Can you see? There is O minus because one of the double bonds have been broken and the electrons have been moved onto oxygen. So I'm going to have O minus, and this time I'm going to have a double bond CH2. You see how it is? Very interesting. So I've just shown you only one of the resonance stabilization. As time goes on and we reach a place where we have to do resonance stabilization, I'll just tell you that this thing can undergo resonance stabilization so that we can move on. Else I'm going to waste a whole lot of spaces showing the resonance stabilization. So now these electrons will come back again to form the double bond, because there is one property that I should let you know. The compounds that are having the carbonyl group, most of them, after nucleophilic addition, they tend to restore back their sp3, so meaning one of the groups should leave so that they could assume their sp2 geometry. All right, so when we get there, we'll still talk about it more. So when this thing happens, the carbon will be forming 5 bonds again, which is not possible. So then one of the bonds is supposed to be broken. Instead of it falling back to carbon, the moment you put an arrow falling back onto carbon, you do an arrow like this, then this is that you are repeating whatever that we've done here, which is not supposed to be the case. So instead of the electrons being bonded, being fallen onto this carbon to generate your carbanion again, we just move straight forward because you are reacting it in the presence of iodine, right? We are going to have the bonding electrons attacking one of this iodine molecule, atom rather. Then the electrons will fall onto this. We are going to generate a lot of I minus in the solution. So now let's move. So from here we are going to have CH3, CH2, and now double bond. Now I'm having CH2 bonded to I. Right, so now we are generating a lot of bases, because you know what can happen when this thing happens. You are going to have your sodium is also going to react with the Ni minus to give you sodium iodide, because we are generating I minus, and also we are having Na plus also in the solution, so it's going to generate sodium iodide. So a lot of them. So the more we are removing iodine, attaching it to the alpha carbon. Sorry, I didn't explain alpha carbon, right? Alpha carbon is actually the carbon that has been attached to the carbon bonding, double bonded to the oxygen. In a way, the carbon that is attached to the carbon bearing the carbonyl group. So you are going to have NaI, right? So these alpha hydrogens, these are alpha hydrogens because they are the hydrogens that have been attached to this carbon. So here I'm going to have my CH3. Here I'm going to have my CH2. I'm repeating the same thing. Then on this side, my carbon double bonded to oxygen. Here I'm having my hydrogen carbon, all right, hydrogen here, a hydrogen, and iodine. So the same thing that happened, you are still going to have your OH minus. The base will come and remove this, and now electrons will fall onto this. We generate another carbanion, right? This time I'm not going to show any resonance stabilization because you know how it works already. After drawing this, you can determine it. So CH3, CH2. Here I'm having my double bond oxygen, and on this side carbon minus, and I'm having my H and I. So now you can see these electrons on the carbon forming the carbanion can fall back here, and now resonance stabilization, right? But here you are not really interested. So this carbanion itself can still attack another I molecule again. So it can still attack another I, and now we have something like this again. So that's how come we are going to have. So you could see that all the methyl groups are being replaced by all the hydrogens on these alpha carbons will be replaced by iodine as time goes on. We're going to have our CH3, CH2, and then we're going to have our double bond carbon. We are having I2, and then the last hydrogen will be here. You get it? Then in the presence of a base again, remember your bases continue being regenerated, because the moment you have your I minus in the solution, the sodium will go and bind to this I to give you your sodium iodide. From what I showed you here, you are going to have a lot of OH minus being produced. So the more we are having OH minus, the more the iodoform reaction continues. So from here, you are going to have your OH minus removing this hydrogen, and now you are going to generate another carbanion again, and from there you are going to have CH3, CH2, and then you are having your double bonded C minus and your I2. You get it? Then see one of the most interesting thing, you are going to have another I. Because you are using iodine, you're having a lot of iodine in the solution, it will attack this I again, this, and you're going to have our sodium iodide being formed. So a lot of OH minus is being produced. We're going to have our CH3, CH2, and then we are going to have something like this, and our sorry, we are not going to have any hydrogen again. We are going to have only Ci3. You can see all the hydrogens, all the alpha hydrogens have been replaced with iodine. So now when we get to this side, the next thing that we are supposed to do is that a lot of OH minus is still in the solution. So the next thing we are going to do is to react it with an acid, which will provide, because you have a lot of OH minus and we don't have any alpha hydrogens anymore. Remember, we don't have any alpha hydrogens. This one is not a methyl ketone. This is an ethyl group, it's not a ketone, so you can't remove these hydrogens because they are less acidic. Let me try and move it to this side. I'm drawing this same structure here. We're going to have CH3, carbon, hydrogen, hydrogen. You're going to have your carbon, double bond, and you're going to have your CI3, right? These hydrogens are not, they are acidic, but it cannot be deprotonated by this OH minus, because when you're talking about the deprotonation of these hydrogens, even though this carbon is an alpha carbon, you cannot remove these hydrogens. So from there, because you're having a lot of OH minus, this OH minus will attack this carbon, because this is the next electropositive atom. It will attack this carbon, and now you are going to have the oxygen being moved onto this oxygen, and you are going to have the electrons from the pi bond moving onto this oxygen. And then let's see, it's actually an interesting reaction though, if you understand it very well. You're going to have a CH3 bonded to CH2, and now our carbon, this carbon will now be having a single bonded to O minus, and now you're going to have the OH that came, which is a nucleophilic addition. So this side is nucleophilic addition. Don't forget about the terms. Nucleophilic addition. All right, so from there you are going to have your CI3. So what I said earlier is that this was having sp3. The hybridization state of this carbon was sp3. The carbon bearing the double bond, it was sp2 rather, which is the trigonal planar. And now because of this nucleophilic addition, you are having sp3. This becomes unstable because most of the compounds that are having the carbonyl groups, they don't tend to assume sp3. So the moment you're having sp3, these electrons from the oxygen will fall back again. When it falls back, it creates a double bond like your carbonyl group, and one of these groups must leave. This group cannot leave because it is not a good living group. This one is also not a good living group. This one can be a good living group only when it is like water. So when the oxygen is having a positive charge and you're having two hydrogens, that's when this one becomes a good living group. But here we are having it as what, alcohol group, so it will not leave. But this is a good living group because it can live with 8 electrons. So that's how come we are going to have the bond being broken and the electrons will be moved onto this carbon to generate our CH3, CH2, and here we are having our double bond, and then we are having OH. What does it look like? This one looks like a carboxylic acid, right? Which is like propanoic acid. So propanoic acid. I'm almost completing the reaction. So propanoic acid plus your C minus. Remember the electrons fell onto this carbon. So C minus, and you are having 3 of the iodine groups. Do you get it? This is not your iodoform. So now you see this particular hydrogen. Let me try and redraw it here. We are having our hydrogen O, and then I'm having my CH2, CH3. This is the propanoic acid. It's the same thing I've drawn here. Now, because this one is nucleophilic center, it will attract this hydrogen, and now the electrons will fall onto this, so that this one becomes CHI3 plus your carboxylate. Your carboxylate here is what? Your propanoate ion, which is CH3CH2, and then we are having a double bonded oxygen O minus. So this one becomes, because we've removed the hydrogen from there, it becomes a carboxylate ion, and in this case it becomes propanoate ion. So propanoate ion, and then the next thing you are going to have will be iodoform. So this is the iodoform that we are talking about, and it is yellow in color. So CHI3 is iodoform. So now we've generated our iodoform. because of the presence of the methyl ketone. This carbon is arising from the alpha carbon that was being called the methyl ketone. So without this alpha carbon and the alpha hydrogens, you'll not be able to form your methyl ketone. So that brings us to the end of our iodoform reaction. So let me try and zoom out, let you understand everything from here. So this is the beginning of it. So you're having your deprotonation. It gives you your carbanion. It will undergo resonance, and now it will attack this particular iodine molecule. So that's where you have your iodine replacing the high alpha hydrogens one by one. The same thing happens here. Iodine still replaces here. Now we are having two of the iodine. We generate our carbanion. This carbanion will also attack another iodine molecule. Now we are going to have all the hydrogens being replaced by iodine. Now this one becomes sp2, right? But because you're having a lot of OH minus in the solution, because of how it is being regenerated, you are going to have OH minus. OH minus will attack this carbon. This carbon will move the electrons onto this oxygen, and you are going to have sp3. Meanwhile, it was sp2. So now this sp3 is unstable. It will then fall back again. The electrons will fall back onto this. Now your iodoform, or your this particular Ci3, will leave a Ci3 minus, and this one will give you your carboxylic acid. Your carboxylic acid is having OH group here. This a hydrogen that is from the OH group can be deprotonated easily. So you are going to have this Ci3 with the negative charge on the carbon nucleophilic center. It will then deprotonate this hydrogen to give you your iodoform, and now this becomes your propanoate ion or your carboxylate. So that brings us to the end of iodoform reaction.